Somewhere far beyond the soft glow of your bedroom window, in the deep, cold dark between the stars, a single giant star is quietly burning through the last patient hours of a life that has already lasted millions of years. Its heart is a slow furnace where atoms are gently being forged into the very stuff of planets and people, while its outer layers swell so wide that, if it stood where our sun stands, it would softly swallow the orbits of the inner worlds. This is Sleepy Science for a Tired Mind, a sleep documentary made to help you fall asleep fast as the night settles all around you. Tonight, in this gentle documentary for sleep, we follow the long, slow life of a giant star, from the soft, cold cloud where it first stirs, through its long, bright middle years, into the swelling red giant skies of its old age, and onward to the quiet, beautiful endings that scatter new stardust across the universe. These are soothing facts to fall asleep to, drawn from astronomy, from sleepy science, and from the quiet patience of light that has been traveling toward us for tens of thousands of years across the deep, cold, dark. Welcome to Drowsy Discovery. Over the next 2 hours, more than 100 gentle facts will carry you slowly through the long life of a single giant star, from its quiet birth in a cold nebula to its soft, glowing afterlife as a planetary nebula or supernova remnant. There is nothing to memorize, nothing to remember, nothing to hold. Just listen and let your mind drift among these facts to fall asleep to as the wider sky breathes softly above your roof. Have you ever stood outside on a clear, cold night and quietly wondered which of those bright points of light might be a giant star nearing the long, beautiful end of its life? You are not alone in that wondering. If you find yourself returning to these soft, calming bedtime stories of the cosmos night after night, you are warmly invited to drift off with us a little more often, and to share these sleepy science journeys with anyone who could use a softer way to fall asleep. Take a slow breath in through your nose and let it out gently through your mouth, as if you were softly blowing dust off the surface of an old, quiet star. Let your shoulders settle, let your jaw soften, and let the long weight of the day melt slowly into the bed beneath you. Let us begin. A giant star begins its life in a cold, dark cloud of gas and dust drifting between the stars. Long before there is any heat or any light at all, a giant star exists only as a possibility, hidden inside a vast, slow-drifting cloud of cold gas and ancient dust suspended quietly between the older stars of the galaxy. These nurseries are called molecular clouds, and they can stretch across many light years of empty space, holding enough material to one day become hundreds or even thousands of new stars. Inside such a cloud, the temperature is breathtakingly low, only a few degrees above the coldest point in the universe, and the gas drifts slowly, almost asleep. There is no fire here yet, no sound, no warmth, only patience and a soft, waiting stillness across many quiet ages. And from this softest possible beginning, a single, mighty giant star will one day rise, very slowly, from the long, dark, cold quiet of the in-between. The first stir of a star is a soft gravitational pull deep inside that quiet cloud. The first true sign that a star is on its way is something almost too soft to notice: a small region inside the cloud where the gas grows just a little denser than the regions around it. The cause may be a passing shock wave from an old supernova, the slow tug of a nearby star, the gentle pressure of starlight from neighboring suns, or simply the natural patience of gravity working over millions of years. Once that small, denser pocket forms, gravity begins to pull more gas inward, and the pocket grows heavier, and the heavier it grows, the more strongly it pulls. There is no flash, no sudden moment, just a long, soft, inward gathering. To watch it would be to watch a very slow breath drawn into the heart of a vast cold room, the first quiet inward whisper of an unborn giant star, beginning to find itself out of the long, patient dark of the wider sky. A protostar is a baby giant star still wrapped in the warm dust of its birth. As the cloud collapses inward, its center grows slowly hotter and denser until it becomes what astronomers call a protostar, a kind of warm beating heart still buried deep inside a thick cocoon of dust and gas. The young giant star at this point cannot yet shine into the open universe because the surrounding cloud blocks most of its visible light. But it already glows softly in infrared, the gentle warmth that the dust around it carries outward into the wider dark. Powerful streams of gas often shoot from its poles in long, slow jets, like quiet lighthouse beams cutting through the dim nursery and lighting up the cloud from inside. The protostar is not yet a true star, only its very young promise, a soft hidden ember nested inside its first warm blanket, slowly gathering enough mass to one day become a fully grown giant burning openly in the dark. Massive stars form much faster than smaller ones like our Sunday. The more massive the cloud that collapses, the faster a star is born, and giant stars in particular grow up at remarkable speed compared to small, calm ones like our own Sunday. A star similar to the Sun may take roughly 50 million years to settle from a cold cloud into a steady adult, but a future giant star can pass through that same long childhood in only a few 100,000 years. And the very heaviest can be ready in less than 100,000 years. The reason is simply that more mass means stronger gravity, and stronger gravity means a far swifter inward gathering of all the surrounding cold gas. To imagine the difference is a little like watching one snowflake settle gently to the ground while another slides quickly down a steep, smooth slope, both arriving in the same place but along very different lengths of slow, patient cosmic time stretched across the years. The moment hydrogen begins to fuse in the core, the giant star truly comes alive. The true birthday of a giant star is not the moment it begins to glow softly, but the moment its core grows so hot and so deeply compressed that hydrogen atoms can finally fuse together into helium. This special threshold is reached around 10 million degrees. And at that temperature, the long-waiting protostar quietly becomes a real, full-grown star at last. The fusion in its heart now produces a steady outward push of energy that exactly balances the inward pull of its own gravity, and from this calm balance, the star begins to live its long main life. The cocoon of dust around it slowly clears away over many years, and for the first time the new giant shines openly into the wider galaxy. Somewhere out among the constellations tonight, a young giant star is having its very first quiet birthday in the long, dark, peaceful cold of the deep space sky. And from the soft moment of ignition, our journey now turns to the long, bright middle years of a giant star's life. A giant star is defined as much by its mass as by its enormous size. In astronomy, the word giant has a slightly more careful meaning than it does in everyday speech, because a giant star is not only large, but usually also far more massive than ordinary stars. A star is generally counted as a true giant when it holds at least 8 times the mass of our Sun, and the very most massive can carry well over 100 solar masses inside a single shining body. This great weight changes everything about the star's life, from how brightly it shines, to how quickly it ages, to how dramatically it eventually ends its long life. The size of a giant star is then a kind of natural consequence of its mass, because heavier stars need wider, hotter cores to support themselves. So when astronomers speak of giants, they are quietly speaking of two qualities at once, both an immense breadth and an immense inner heaviness, woven softly together inside one single, glowing body. The most massive stars can be more than 100 times heavier than our Sunday. The very heaviest stars known to astronomy are almost beyond comfortable imagination, holding more than 100 times the mass of our Sun packed inside a single luminous body. A famous example, called R136A1, lives inside a great cluster in a nearby galaxy, and is thought to weigh somewhere around 200 solar masses, perhaps even more than that. Such enormous stars are extremely rare because clouds with enough mass to make them are uncommon, and when they do form, they live so briefly that few exist at any one time across the wider galaxy. Each one is a kind of cosmic candle burning thousands of times brighter than our calm yellow sun in the long dark. To picture one is to picture a single soft star somehow holding the weight of 100 suns inside it, glowing fiercely against the long, deep, peaceful dark of the wider universe. Giant stars burn their fuel far faster than any small, quiet star. One of the gentle ironies of the cosmos is that the brightest, mightiest stars also live the shortest lives, because the same great mass that makes them shine so fiercely also forces them to burn through their fuel at an extraordinary rate. A small, calm red dwarf star may quietly drift through tens or even hundreds of billions of years, longer than the entire current age of the universe so far, while a massive giant may shine its fierce blue light for only a few million years before reaching the end. The interior pressures inside a giant are so very high that fusion races forward almost desperately, swallowing hydrogen far faster than its slower, gentler cousins ever do. In this soft sense, every giant star is a kind of brilliant short story, written in light, while smaller stars are long, slow, patient novels still quietly being told by the cool dark of the cosmos. The hottest giant stars glow blue rather than gold or red. The color of a star is in many ways a soft, honest portrait of how hot its surface really is, and the very hottest giants glow not yellow or orange, but a deep, beautiful blue. Their surfaces can reach temperatures of 20,000, 30,000, even 50,000 degrees, far hotter than our familiar yellow sun, which sits at only about 6,000 degrees by comparison. At such fierce heat, the light a star pours out shifts toward the shorter blue end of the spectrum, giving these massive bodies a color somewhere between sapphire and ice on a clear winter night. To look up at the night sky and find a calm, sharp blue point of light is often to look at a young blue giant or supergiant burning thousands of times brighter than our sun, even when its great distance softens its glow into a small, bright jewel quietly resting in the dark of the sky tonight. A blue supergiant can shine as bright as 1,000,000 suns at once. Among the very brightest stars in the universe are the blue supergiants, fierce young giants whose surfaces blaze with heat and whose total light output can rival 1,000,000 ordinary suns combined into one single body. Stars like Rigel and Orion, or the famous bright members of the cluster around R13601, pour out so much energy that even from thousands of light years away, they remain easily visible to the unaided human eye. If our own sun were quietly replaced with such a body, the sky would become unrecognizable, the inner planets would be quickly stripped of their atmospheres, and the long calm of our solar system would end in a single bright moment. Yet from a great safe distance, in the soft hush of this sleep documentary, these blue giants become only beautiful, faraway points of light, gently anchoring entire constellations across our night sky. And from the quiet brilliance of these blue giants, our path now drifts gently toward the inner workings of a star's slow, patient heart. The core of a giant star is a slow furnace forging new elements every second. At the very heart of a giant star, deep beneath layer upon layer of glowing gas, sits a slow furnace where new chemical elements are quietly being made one at a time. The fusion that happens there does not only release energy, it also welds smaller atomic nuclei into larger ones, building heavier and heavier elements over the long course of the star's life. Hydrogen becomes helium first, and over millions of years, helium is fused into carbon, then oxygen, then neon, then silicon, each step needing higher temperatures and a more compressed core. To imagine this is to imagine a soft, ancient blacksmith working in deep silence inside the star, patiently shaping the future raw material of planets, of mountains, of oceans, and even of the elements that will one day quietly come together to form a sleeping body curled beneath a warm blanket far away. The pressure at the center of a giant star is almost beyond imagining. The pressure at the center of a giant star is something the human mind can only approach softly, never fully grasp, because it lies so far beyond any pressure ever felt on Earth. The weight of all the layers of gas above the core presses down with a force so enormous that the matter at the center is squeezed into a state denser than any solid we know in our daily lives. Atoms there are stripped of their electrons, and the gas behaves more like a glowing soup than anything familiar to the surface world. Yet despite that ferocious pressure, the inside of the star remains in a kind of long, calm balance, because the outward push of fusion energy holds the inward weight gently in check. It is a slow, hidden equilibrium, a soft and patient peace held quietly inside an unimaginable storm of light, lasting across many millions of slow, glowing years deep within the star. Energy from the core takes thousands of years to reach the surface. The energy born in the core of a star does not rush instantly outward to its surface, but instead drifts slowly through the thick layers of glowing gas in a long, patient journey that can take many thousands of years from beginning to end. Each photon of light is absorbed and re-emitted countless times by the dense matter around it, bouncing slowly outward like a wandering traveler crossing a vast, foggy plain. Inside our own sun, this journey is thought to take somewhere between 100,000 and a few 100,000 years, and inside a giant star with even denser interiors, the path can be longer still. So the warmth of starlight you feel today on a quiet evening was, in some sense, born inside the star long before any human civilization existed. Light is patient, deeply patient, in the long quiet of the cosmos, drifting outward across uncounted ages. The light you see from a distant giant star left it long before you were born. When you look up at a distant giant star tonight, the soft point of light arriving in your eyes is far older than the moment of looking, and very likely far older than you yourself. The light from a star, 1,000 light years away, has been traveling toward you for 1,000 years, slipping silently across the dark of space the entire time. The light from a giant star 10,000 light years away set out long before history was written down on Earth. So, the sky above you is, in a soft sense, not the present at all, but a slow and beautiful gallery of the past, painted in starlight that began its journey long before you were born. To rest beneath such a sky is to lie quietly inside a kind of cosmic memory, gently held by the very old light of distant suns whose own moments of brightness long ago drifted softly outward into the dark, finding your patient eyes after many quiet years of long, silent travel. Every giant star is held together by the soft, patient pull of its own gravity. Every giant star, no matter how fierce or how bright, is held together by something almost tender at heart, the slow, patient pull of its own gravity drawing every part of itself toward its center. Without this constant inward embrace, the heat of the core would scatter the star's outer layers into space within mere days. With it, the great body remains a single rounded shape, breathing softly between the outward push of fusion and the inward call of mass. In a way, gravity is the long, quiet song the star sings to itself across millions of years, the simple and devoted music of holding its own form together. To picture it is to picture a vast, glowing body resting in the dark, kept whole by the same invisible force that gently keeps a sleeping body settled into a soft mattress on a calm night. The quiet pull that draws all things home in the long, calm dark. And as you rest with these gentle facts to fall asleep to, there is no need to hold any of them tightly. Let them drift through you like quiet starlight passing through a window. Take a slow, soft breath and let your body settle a little deeper into the bed beneath you. The size of a giant star can be hundreds of times larger than our Sunday. The size of a giant star is one of the most quietly humbling facts in all of astronomy, because the largest examples are not just bigger than the Sun, they are hundreds and sometimes more than 1,000 times wider across. A typical red supergiant might span 500 to 900 times the diameter of our familiar yellow Sunday. The truly enormous ones, like UI Scuti or Stephenson 2 to 18, are estimated to reach over 1,000 times the Sun's width, which is hard for any human imagination to truly hold. To picture this gently, imagine our own Sun as a small marble resting calmly in the palm of your hand. A giant star of that size, on the same scale, would be a soft, glowing globe wider than a small house, gently filling an entire quiet room with a warm, slow, patient light that drifts softly across every corner of the still, dim space around it. If a red supergiant stood where our Sun stands, it would swallow the inner planets. If a red supergiant such as Betelgeuse or Antares were quietly placed where our Sun stands today, the inner planets of our solar system would simply vanish inside it, swallowed by the soft outer layers of the star. Mercury would be lost first, then Venus, then Earth, and even Mars would lie deep inside the glowing surface, all silently absorbed, without leaving a trace. The outer edge of such a giant could reach far past the orbit of Jupiter, and in the case of the very largest known supergiants, even further still. This is not described to frighten, but to softly mark the scale of what these stars truly are. The sky we see is full of bodies so vast that whole solar systems could rest comfortably inside a single one of them, glowing slowly in the calm distance of the night, each one a quiet world of its own kind of slow, ancient cosmic time. Some giant stars are so large that light takes hours to cross them. Some giant stars are so large that even light, which crosses the entire Earth in less than 1/10 of a second, takes hours to travel from one side of the star to the other. Light needs only about 5 seconds to cross the diameter of our Sun, but a star like Stephenson 2 to 18 is thought to be more than 2,000 times wider, meaning a beam of light would need many hours to journey across its full body. Inside such a body, distances feel almost planetary in scale, and yet the entire vast structure is still a single unified glowing star. To imagine it is to imagine a slow golden sea of plasma so wide that even the fastest thing in the universe must take its long, patient time to cross from one calm shore to the other in the long, quiet, dark, drifting slowly through the soft, deep silence of space far away from any human shore tonight, glowing on quietly in the long, calm dark. The surface of a giant star is not solid like the surface of a planet. The surface of a giant star is not solid, the way the surface of a planet like Earth or Mars is solid, but is instead the soft outer layer of a vast glowing sphere of gas. There is no ground to stand on, no rock or sand or shore, only a slow, blurred boundary where the star's atmosphere becomes thin enough for light to escape into open space. Astronomers call this layer the photosphere, the level from which most of the star's visible glow finally reaches the wider universe. Inside the photosphere, enormous bubbles of hot gas rise and fall in slow waves, very much like the surface of a gently simmering pot, only on a scale far beyond any human kitchen. To picture the surface of a giant star is to picture a soft, glowing ocean of plasma, slowly breathing under its own quiet weight, rising and settling in long, ancient waves across the calm distance of the dark. Giant stars often pulse slowly, growing and shrinking over many days. Many giant stars do not shine with a perfectly steady light, but pulse very slowly, growing a little larger and a little smaller across many days, weeks, or even years. The whole star expands as its outer layers swell outward under fusion pressure, then contracts again as gravity slowly pulls them back in, creating a long, calm rhythm of breath-like motion. As the star pulses, its brightness rises and falls gently in a pattern that astronomers can carefully measure from Earth, sometimes over decades. These pulsating giants are called variable stars, and Betelgeuse is one of the most famous of them. To imagine such a star is to imagine a vast glowing chest slowly rising and falling in the deep silence of space, breathing in long, peaceful intervals that may last as long as a single human lifetime. Sometimes even longer than that, slow and steady in the patient dark. And from the soft pulsing of these vast bodies, our journey now turns to the famous giant stars that decorate the sky we see from Earth. Betelgeuse is one of the most famous red supergiants in our night sky. Betelgeuse is one of the most beloved giant stars in the entire night sky, the bright orange shoulder of the constellation Orion the Hunter, easily visible to the unaided eye on a calm winter evening. It is a red supergiant, perhaps 800 to 900 times wider than our own Sun, and it sits roughly 650 light-years from Earth in the cool dark of the galactic neighborhood. Its color is a soft, warm orange that contrasts gently with the cooler blue-white light of its companion Rigel below. Betelgeuse pulses slowly, brightening and dimming over many months, and astronomers know that one distant day, perhaps in the next 100,000 years or so, it will end its life in a great supernova. A brief but spectacular farewell, quietly visible from across the galaxy on a clear, calm winter sky filled with old, patient light slowly drifting down toward our small, sleeping world. Betelgeuse marks the shoulder of the constellation we know as Orion. The constellation Orion is in many ways a soft gallery of giant stars, with not just Betelgeuse on its shoulder, but Rigel at its foot, Bellatrix at the other shoulder, and the bright belt and sword stars at the center. All of them massive and luminous compared to our calm yellow Sunday. Together, they form one of the easiest patterns to find in the night sky, especially on cold winter evenings in the northern half of the world. The Hunter has been recognized by many cultures for many thousands of years, and most of the bright points that draw his shape are powerful giants in different stages of their long lives. To rest your eyes on Orion is to look quietly at a single small frame of sky filled with some of the most magnificent giant stars currently glowing softly in our galaxy. Each one a slow story of mass and light written gently across the dark of the wider winter sky. Antares is a red supergiant that glows in the heart of Scorpius. Antares is another famous red supergiant, the bright reddish heart of the constellation Scorpius, low in the southern sky during summer evenings in the northern half of the world. Its name comes from ancient Greek and means rival of Mars because its warm orange-red color reminded early sky watchers of the planet Mars when the two appeared near each other. Antares is roughly 700 times wider than our Sun, and it lies about 550 light-years from Earth in the cool dark of the galaxy. Like Betelgeuse, it pulses slowly across long stretches of time. To find Antares low on a quiet summer night is to find one of the great old hearts of our galactic neighborhood, glowing softly with the warm, patient light of a dying giant near the gentle end of its long life. Drifting calmly through the patient deep dark of space far away from any small sleeping world. Rigel, the bright blue jewel of Orion, is also a giant star. Rigel, the bright blue-white foot of Orion, is a beautiful contrast to the warm orange of Betelgeuse, glowing with the cool, sharp light of a young, hot blue supergiant. It is roughly 21 times the mass of our Sun, but shines somewhere around 120,000 times more brightly, pouring out its light from a surface temperature near 12,000 degrees. Rigel sits about 860 light-years from Earth, and although that is greater than the distance to Betelgeuse, it actually appears slightly brighter in the sky because it produces so much more total light. To watch Orion rise on a clear winter evening is to see a soft, slow conversation between two giants, one warm and old and dying, the other young and blue and still in the long, fierce middle of its bright. brief life across the calm dark above us tonight, both glowing peacefully across the same wide winter window of sky. Deneb in the constellation Cygnus shines from thousands of light years away. Deneb is the brilliant tail of the great northern bird Cygnus the swan, a blue-white supergiant so luminous that even from a distance of perhaps 2,500 light years, it remains one of the brightest stars in our entire night sky. Astronomers estimate that Deneb shines around 200,000 times more brightly than our calm yellow sun, although precise measurements remain difficult because of its great distance. It is one of the three stars of the Summer Triangle, together with Vega and Altair, easy to find on warm, calm evenings when the band of the Milky Way arcs softly overhead. In this sleep documentary about giant stars, Deneb is the gentle reminder that some of the brightest points we see in the night are also among the most distant, glowing patiently across enormous gulfs of quiet, dark space that even the patient light has needed many ages to softly cross. And from the familiar names of these bright sky giants, our path now turns to the rare stars that push the very edges of size and brightness. UY Scuti is one of the largest known stars in the entire Milky Way. UY Scuti is one of the largest stars currently known to astronomy, a red supergiant resting deep in the constellation Scutum, somewhere around 5,000 light years from Earth in the cool dark of the inner galaxy. It is estimated to be more than 1,700 times wider than our own Sun, although measurements of such distant pulsing giants always carry some gentle uncertainty. If UY Scuti were quietly placed where our Sun sits today, its outer surface would extend far past the orbit of Jupiter, perhaps reaching toward the orbit of Saturn. The star is so vast that an aircraft flying at normal cruising speed would need many thousands of years simply to circle around it once. To imagine UY Scuti is to imagine a star wide enough to hold an entire planetary system gently inside its own glowing body, a slow, soft sphere of plasma drifting calmly through the long, dark cold of the wider galaxy. Stephenson 2-18 is so vast it dwarfs nearly every other known giant. Stephenson 2-18 is another truly enormous red supergiant, often discussed alongside UY Scuti as one of the largest known stars in the universe, lying inside a distant cluster more than 19,000 light-years from Earth. Some estimates place its diameter at over 2,000 times that of our Sun, although the great distance and thick interstellar dust between us make precise measurement difficult. If Stephenson 2-18 were placed where our Sun stands today, its outer edge could possibly reach beyond the orbit of Saturn, an almost dreamlike scale to consider quietly. Stars of this size sit near the upper limit of what astronomers believe a stable star can be. To picture this is to picture a soft glowing giant so wide that even our familiar planetary neighborhood would simply rest tucked gently inside it, far inside its calm, bright body, held by the patient pull of its own gravity in the deep dark. Eta Carinii is a violently bright giant wrapped in clouds of its own dust. Eta Carinii is one of the most fascinating and unstable giant stars in the galaxy, a massive system roughly 7,500 light-years away in the southern constellation Carina. It contains at least two stars, the larger of which holds perhaps 100 times the mass of our Sun, making it one of the heaviest stars in our cosmic neighborhood. In the 1800s, Eta Carinii underwent what astronomers call its Great Eruption, briefly becoming the second brightest star in the entire night sky before slowly fading from naked eye view. The eruption shed two enormous lobes of glowing gas, now known as the Homunculus Nebula, slowly drifting outward across centuries. Eta Carinii is widely thought to be moving toward an eventual supernova, a quiet certainty waiting somewhere in its long, bright future, slowly approaching across the gentle ages of cosmic time. R13601 is one of the most massive stars ever measured, far heavier than our Sunday. R13601 lives at the center of a great star cluster called R136, deep inside the Tarantula Nebula in the Large Magellanic Cloud, a small companion galaxy of our own Milky Way. It is widely considered the most massive star ever measured, holding around 200 solar masses, although it is slowly losing weight through powerful stellar winds streaming outward into space. The star also shines with extraordinary brightness, somewhere around 6 million times more luminous than our calm yellow sun, although much of its light pours out as ultraviolet rather than visible glow. R13601 is too distant to see with the unaided eye, but in the soft language of astronomy, it stands quietly as one of the most impressive single objects ever discovered in the deep dark of the wider universe. Glowing patiently far beyond the reach of any unaided human eye on a calm Earth night. Wolf-Rayet stars shed their outer layers in soft, glowing winds. Wolf-Rayet stars are a special and rare class of giant stars, very massive bodies that have already shed much of their outer layers through powerful, fast-streaming stellar winds. What remains is the hot exposed core of a once larger star, glowing fiercely at temperatures that can exceed 100,000 degrees on the surface, sometimes far more. These stars pour out enormous amounts of energy, and their winds carry away mass at a remarkable rate, slowly stripping the star down toward its eventual end. As you rest tonight in the soft hush of the night, somewhere in the galaxy a Wolf-Rayet star is quietly losing perhaps a sun's worth of mass every 100,000 years or so, slowly preparing itself for an eventual supernova whose echoes may one day enrich the slow, calm material from which new worlds will form long after we have all gone gently to sleep. And from these extreme restless giants, our journey now turns to the long, calm middle years of an ordinary giant star's life. The main sequence is the long, stable middle of a giant star's lifetime. The longest, most stable chapter of any star's life is called its main sequence, the slow and patient middle stretch of years during which it quietly fuses hydrogen into helium deep in its core. For our own sun, this main sequence will last roughly 10 billion years in total, of which we are currently about halfway through. For a giant star, the same chapter is far shorter, often only a few million years from beginning to end, because the heavy weight of the star pushes its core into much faster fusion. Yet within that brief stretch of time, the giant lives in a kind of long, calm equilibrium, glowing steadily without much change. Most of the stars you see in the night sky tonight are spending their long, quiet middle years here on the main sequence, gently shining their patient light far across the dark of the wider galaxy and the silent space between worlds. During the main sequence, hydrogen quietly turns into helium in the core. Inside the core of any main sequence star, the same essential process is quietly taking place, the slow, patient fusion of hydrogen nuclei into helium nuclei, releasing a small amount of energy with every reaction. In smaller stars like our Sun, this fusion happens through a chain of reactions called the proton-proton chain, which works softly at relatively low core temperatures. In giant stars with hotter, more compressed cores, fusion follows a faster pathway called the carbon-nitrogen-oxygen cycle, in which heavier nuclei act as gentle catalysts. The result is the same in both cases, hydrogen slowly becoming helium and starlight gently flowing outward into the cosmos. To picture it is to imagine a soft, ancient kitchen inside the star, slowly turning one simple ingredient into another over many millions of long, calm years of patient inner cosmic time. A massive giant star may spend only a few million years on the main sequence. The main sequence life of a giant star is shockingly brief by cosmic standards, often lasting only a few million years from the moment fusion begins to the moment its core finally runs short of hydrogen. By contrast, a small calm red dwarf may sit on the main sequence for hundreds of billions, even trillions of years, longer than the present age of the universe many times over. Our own sun lies somewhere in between, with its main sequence lasting around 10 billion patient years from beginning to end. The heaviest giants pass through this same long chapter in less time than a single galactic year, the time it takes our Sun to orbit the center of the Milky Way once. To imagine a giant star is to imagine a brief, brilliant flame burning inside the much longer, slower candlelight of the wider cosmos, a quick, bright moment held softly inside an enormous patient ocean of cosmic time. Despite their huge fires, giant stars live far shorter lives than tiny ones. Because giant stars live so much shorter lives than smaller stars, every giant we see in the night sky is by definition relatively young in cosmic terms. A red dwarf burning gently nearby may have been quietly shining for 10 billion years, but a blue giant gleaming above us tonight cannot be more than a few million years old, perhaps even less. This means giant stars are usually still found near the cool dust clouds where they were born, often grouped together with their many siblings in star-forming regions or open clusters. The bright stars of Orion, for example, are all relatively young by cosmic standards. To look up at a young giant is to look at a star that has barely begun its long story, even though that story will end far sooner than the calm, patient lives of its smaller, gentler cousins quietly drifting nearby across the deep, dark sky. The brightest stars in the sky are nearly always among the youngest. Among the brightest stars visible from Earth, almost all of them are giants of one kind or another, even though giants are quite rare compared to small, dim red dwarfs. The reason for this is simply that the very brightest stars stand out across enormous distances, while small, dim ones can only be seen if they are very close to us. So the night sky we know best is in many ways a sky shaped by the loud light of the rare giants, with their many smaller cousins quietly hidden in the gentle background. The everyday sun is in this sense an unusual sight in the night sky because it is one of the more typical, smaller, calmer stars rather than one of the bright few. To look up is to see, again and again, the great rare bodies glowing softly across the long, dark galaxy above the patient, still surface of our calm, sleeping world below the slow, ancient turning of the wider sky. And from these soft, steady middle years, our path now turns toward the slow turning point when a giant star begins to change. When the hydrogen in the core runs low, a giant star begins to swell. When a giant star finally begins to run low on hydrogen in its core, it does not simply fade quietly away. Instead, the star slowly swells outward, growing larger and larger as its outer layers expand under the changing balance of pressure and gravity inside. Over the course of a few 100,000 years, a star that once shone as a bright, compact body can become a vast, distended sphere many times its earlier size. The surface drifts further from the heart of the star, which means the same energy spreads out across a much larger glowing area. The whole star takes on a softer, swollen, almost dreamlike form, slowly transforming into the shape we recognize as a red giant or red supergiant, a familiar quiet ending for stars across the long, red supergiant. Calm galaxy of cosmic time, slowly drifting toward the soft red end of their long, bright lives in the patient hush of the wider, deepening dark. As the outer layers expand, the surface cools and the color shifts toward red. As the outer layers of an aging giant star spread outward, the same total energy is shared across a far larger surface, and the surface itself slowly cools as a natural result. Cooler stars glow with longer, redder wavelengths of light rather than the sharper, hotter blue and white tones of younger stars. So an aging giant naturally drifts toward an orange and then a deep red color as it grows old, becoming what astronomers call a red giant or red supergiant in the final long chapter of its life. The star is still pouring out enormous amounts of energy, sometimes more than it ever did in its youth, but spread so thinly that its skin shines softly red. To picture a red supergiant is to picture an old, vast, glowing autumn coal slowly cooling in the deep, calm dark of space, glowing on patiently across the silent ages of the long galactic night. A red giant, or red supergiant, is a star deep into the autumn of its life. In a soft and poetic sense, a red giant is the autumn season of a star, the long, warm orange chapter that comes between the bright summer of its main sequence and the deep winter of its eventual ending. The color itself reminds many cultures of falling leaves, of late afternoon sunlight, of the gentle slowing down that comes near the close of any long, patient day. Astronomers, of course, describe these stars in careful physical terms, but the seasonal image fits the soft truth of their life cycles. To watch a red giant in the night sky is to look at a quiet old being, slowly cooling, slowly preparing itself for what lies ahead. There is no fear in this image, only a kind of warm acceptance, the quiet beauty of a body softly arriving at the long, calm twilight of its own great cosmic year, glowing patiently far above the still surface of our small sleeping world tonight. Inside the swollen star, helium begins to fuse into heavier elements. When the hydrogen in the core of a giant star is finally exhausted, the core itself slowly contracts under its own gravity, growing hotter and denser until a new kind of fusion begins. At about 100 million degrees, helium nuclei start to fuse together into carbon and oxygen, the next gentle step in the long chain of stellar nucleosynthesis. This new fusion releases fresh energy, briefly steadying the star into another, shorter chapter of stable life. In smaller stars like the Sun, helium burning is the final main fusion stage, but in giant stars it is only the next stage of many. To imagine helium burning is to imagine the star quietly relighting its inner furnace with a new fuel after the first one runs low, slowly continuing its long, patient story for a little while longer in the dark, glowing softly across the calm distance of the wider sky above. Layer by layer, the giant star builds carbon, oxygen, neon, and beyond. In a giant star, the slow story of fusion does not stop at carbon and oxygen, because the core can grow hot and dense enough to fuse heavier elements still, one careful step at a time. After helium burning ends, carbon and oxygen begin to fuse into neon, then magnesium, then silicon, each new stage requiring even higher temperatures and shorter spans of time. While hydrogen burning lasts millions of years, neon and silicon burning may last only days. In this sleep documentary about giant stars, that picture is a quiet reminder that the heavier elements of the periodic table are not made anywhere on Earth, but inside the slow, glowing furnaces of dying massive stars, gently forging across long and shortening years, the very atoms that one day will gather to form planets and oceans and patient, breathing bodies far away from the stars that first quietly forged them. And as you rest with this slow, patient story of a star, there is nothing for you to do tonight. Let your shoulders soften, let your hands fall open, and let these sleepy science facts gently carry you a little closer to deep sleep. The inside of an old giant star is layered like the rings of a quiet onion. By the late stages of its life, a giant star quietly takes on the structure of a great cosmic onion, with many concentric shells of different fusion reactions burning gently around its inner heart. The outermost layer is still hydrogen, slowly fusing into helium, while the next inward shell burns helium into carbon, then carbon into neon, then neon into oxygen, then oxygen into silicon, and finally silicon into iron at the very center. Each layer burns its own fuel at its own temperature, and each grows hotter and denser the deeper one looks, like the rings of a glowing ancient tree. To imagine such a star is to imagine a slow, vast, layered furnace of the universe, with each shell quietly carrying out its own ancient work in the long, patient dark of space, far above any sleeping world, glowing on across the silent ages of cosmic time deep in the wider sky. The very last layer of fusion in a massive star creates iron in the core. At the very center of an aging giant star, an iron core slowly grows, a small, dense, glowing heart of pure iron and nickel quietly built up from all the fusion stages that came before it. The core itself may be only the size of a planet like Earth, yet it can hold roughly the mass of our entire Sun packed inside that small body. The pressure and density there are almost unimaginable, and the temperature reaches billions of degrees during the final hours. This dense iron core sits at the calm center of all the still glowing shells around it, the final, quiet inner endpoint of the long fusion story. To picture it is to picture a small, fierce, unyielding seed slowly growing inside the long, ancient body of the dying giant star, deep in the silent dark of the wider galaxy, slowly waiting for the long, quiet moment that will close the star's old story. Iron is the soft full stop of a star's long, fiery sentence. Iron is in many ways the soft full stop at the end of a giant star's long fusion story, because fusing iron does not release energy the way lighter elements do. Instead, fusing or splitting iron actually absorbs energy, which means the iron core cannot keep itself warm by burning the way the layers above it can. As iron piles up at the center of the giant star, the inner pressure that has long supported the body against gravity slowly begins to fail. The core grows heavier and heavier, but no new fusion can rescue it, and the long, calm balance that has held the star together for millions of years finally begins to give way. Iron, the patient inner ash of all those earlier fusion stages, is the slow, quiet ending the star has been riding toward all this time across many millions of long, glowing years of patient, layered cosmic work deep in the still heart of the giant. Stellar winds gently strip mass from the surface of an aging giant star. Long before its end, a giant star already loses huge amounts of mass through soft, outflowing winds of charged gas, slowly streaming away from its surface and out into the cool, dark space around it. These stellar winds can carry away the equivalent of an entire Earth mass every few years, and across millions of years they can strip many solar masses of material from a single body. The lost gas drifts outward and gradually mixes with the wider interstellar medium, gently enriching the cosmic clouds from which new stars and worlds will one day form. To imagine these winds is to imagine a slow, soft exhalation, the giant star quietly breathing some of itself out into the larger universe across enormous spans of time, very patiently giving its own substance back to the calm body of the wider galaxy across the long, slow ages of patient cosmic time and the slow turning of the deep, dark night above. Some red supergiants lose enough mass to wrap themselves in soft, glowing shells. Many red supergiants are surrounded by soft, expanding shells of gas and dust that they have shed over the long course of their old age. Very faint glowing nebulae traced gently by the star's own slow winds. From a great distance, these shells look like quiet halos of light around the star itself, almost like soft breath slowly moving outward into the dark. Astronomers can study these shells to learn about the chemical history of the star, because each shell carries traces of the elements forged inside the giant during different stages of its long life. To imagine such a star is to imagine an old, soft, glowing body wrapped in the layered, ghostly memory of all its earlier years, very gently drifting outward into the wider, ancient galactic sky around it tonight, glowing softly across the long, patient cold of the deep cosmic dark of the wider universe. And from the quiet shedding of those outer layers, our journey now turns to the dramatic but distant endings that wait for the heaviest stars. When iron fills the core, the giant star can no longer hold itself up. When the iron core of a giant star finally grows too heavy to support its own weight, the long, calm balance inside the star fails completely, and the core collapses inward in a fraction of a second. Gravity pulls the matter at the center into a body so small and so dense that the inrushing layers above it bounce violently outward in a tremendous, expanding shockwave of energy and light. This event is called a core collapse supernova, and it marks the end of the giant star as we knew it, while at the same time releasing more energy in mere days than the Sun will release in its entire 10 billion-year lifetime. The supernova is the soft yet enormous farewell of a giant star, the slow, quiet completion of all its long, patient inner work across the silent, dark, gently writing the final sentence of a story many millions of years in the slow making, far above the calm, sleeping world. In a fraction of a second, the core collapses inward upon itself. The collapse of a giant star's iron core happens with breathtaking speed, taking only a small fraction of a single second from beginning to end. In that brief moment, the inner core is squeezed from the size of a planet down to a body perhaps just 20 kilometers across, while temperatures soar into the hundreds of billions of degrees. The matter at the center is compressed so tightly that protons and electrons are forced together to form neutrons, releasing a vast flood of nearly massless particles called neutrinos. These neutrinos carry away most of the supernova's enormous energy, drifting outward through the body of the dying star at almost the speed of light. The visible explosion that follows is in many ways only a soft, beautiful echo of this brief, very quiet inner collapse hidden deep inside the star, drifting outward in long ripples of light across the long, calm dark of space and time. The collapse triggers one of the brightest events in the universe, a supernova. A supernova is one of the brightest events that occurs anywhere in the universe, briefly outshining the entire galaxy in which it happens, including all of its hundreds of billions of other stars combined. For a few weeks, a single dying giant can pour out more visible light than every other star in its home galaxy taken together. From distant Earth, even a supernova in a faraway galaxy may briefly become visible to the unaided human eye, gently appearing as a new soft point of light in the night sky where none was seen before. Astronomers carefully record such events, knowing they are watching the very end of one giant star's long, patient life. The brilliance fades after weeks and slowly drifts back into the steady, soft glow of the wider galactic dark sky, leaving behind only a quiet, expanding cloud of memory in its place across the long, patient ages. A single supernova can briefly outshine an entire galaxy of normal stars. In the moment a giant star explodes as a supernova, it briefly shines with a brightness of perhaps 10 billion suns, all packed into a single fading point of light somewhere out in the vast galactic sky. The light from such a distant event can travel for thousands or millions of years through space before quietly arriving at our eyes, sometimes long after the star itself has finished its slow farewell. Some of the supernovae we see in the sky tonight may have actually exploded long before the time of the dinosaurs, their soft, far light still gently arriving from those very ancient cosmic moments. To watch a supernova is in this sense to watch a small piece of very deep cosmic history slowly arriving at our patient world from far across the long, quiet dark of the wider universe, gently finding our small, calm planet after long drifting ages of pure, silent travel. Supernovae scatter newly forged elements far across the cold, dark space. In the great burst of a supernova, the dying giant star scatters all the elements it has forged across its long life out into the cool, calm dark of space, gently enriching the wider galaxy with carbon, oxygen, silicon, iron, and many other heavier atoms. Some of these elements drift for many millions of years through the cool clouds between the stars, slowly mixing with the older gas and dust until they help form new stars and new planets. The carbon in your own body, the oxygen in every breath you take, and the iron in your blood were all once forged inside the deep core of an old giant star and gently scattered into space by a quiet supernova long before the Earth was even born. You carry pieces of long-lost giants quietly inside you tonight, soft cosmic ash patiently woven into every breath you take and every soft beat of your own slow, sleeping heart. And from the bright, distant flash of a dying giant, our path now turns gently toward the soft echoes such an event leaves behind. The Crab Nebula is the glowing remnant of a supernova seen nearly 1,000 years ago. The Crab Nebula is one of the most studied supernova remnants in the entire night sky, the slow expanding wreckage of a massive giant star that ended its life in a spectacular explosion long ago. The original supernova was witnessed and recorded by Chinese, Japanese, and Arab astronomers in the year 1054 when it appeared as a brilliant new star bright enough to be seen during the day for several weeks. Today, almost 1,000 years later, the gas from that explosion is still expanding outward at thousands of kilometers per second, forming the soft, tangled threads of light we now call the Crab. At the very heart of this glowing nebula spins a small, dense neutron star, the quiet final remnant of the original giant star's collapsed inner core, deep in the dark of the wider winter sky, slowly turning across thousands of patient cosmic years. Ancient skywatchers in many cultures recorded the supernova that made the Crab Nebula. Long before modern astronomy, ancient skywatchers across many cultures noticed when bright new stars suddenly appeared in the night sky and then slowly faded away over weeks or months. They called these stars guest stars or new stars, and their patient records of these rare events have given modern astronomers important clues about supernovae that occurred long ago. The famous supernova of 1072, which left behind the soft Tycho remnant in the constellation Cassiopeia, the supernova of 1404, and the Crab supernova of 1054 are all gently remembered through these old written observations. To know that observers 1,000 years ago quietly looked up at the same sky and saw the death of a giant star is to feel a calm thread of human attention drawn quietly across many centuries of patient time, joining the present and the past in a single shared upward glance. Supernova remnants can keep glowing softly for tens of thousands of years. The visible light of a supernova fades after a few months, but the expanding cloud of gas it leaves behind, called a supernova remnant, can remain glowing softly for tens or even hundreds of thousands of years. These remnants slowly grow outward through space, gently sweeping up the cool surrounding gas and dust into beautiful, layered, shell-like shapes. The Veil Nebula in the constellation Cygnus, for example, is the slow remnant of a supernova that may have happened around 10,000 years ago, and its delicate filaments still glow tonight in soft reds and greens and blues. To watch a supernova remnant is to watch a slow, soft, expanding memorial to a single giant star gently blooming across light years of space, drifting outward through the long, dark calm of the surrounding galactic sky, glowing softly across light years of slow, patient cosmic distance. The shock waves from a supernova can quietly compress nearby clouds into new stars. Supernovae do far more than enrich the wider galaxy with new elements. They also send out powerful shock waves that travel through the cool clouds of gas and dust around them, gently squeezing those clouds and sometimes triggering the slow birth of new stars. When a shock wave reaches a quiet molecular cloud, it can compress small regions just enough to start the inward gravitational collapse that begins the long story of star formation all over again. In this soft sense, every supernova both ends one chapter and quietly begins another, sending out the gentle nudge that will give rise to a new generation of suns and worlds. The death of a single giant can be the patient, invisible cause of many distant young stars beginning to glow softly in the long, slow ages of the cosmic dark to come, gently sparking new beginnings far across the wider sky. In this way, the death of one giant star helps gently give birth to the next. Through the patient eye of modern astronomy, and especially through the soft framing of this sleep documentary, the death of a single giant star is never only an ending, but always also a quiet beginning somewhere else in the wider galaxy. The atoms scattered by one supernova drift through the cool dark for many millions of years, eventually gathering into new clouds, new young stars, and even new planets where soft oceans and gentle breaths may one day quietly arise. The shockwave from that same explosion may help to spark the very first inward collapse of those new clouds across the long, slow ages to come. So, in the long, calm story of the cosmos, every old giant star is in some way the slow, patient grandparent of a future star or world, gently giving its own substance forward across the long, deep ages of cosmic time and the wider, slowly drifting body of the calm, quiet galaxy. And from these soft, glowing echoes, our journey now turns to the strange, dense remnants that can be left behind in the heart of a fallen giant. A neutron star is the impossibly dense core of a fallen giant star. At the center of many supernova remnants quietly sits a neutron star, the small, incredibly dense remains of what was once the iron core of a giant star. A neutron star may hold somewhere around 1.5 times the mass of our Sun, but it is squeezed into a body only about 20 kilometers across, roughly the size of a small city on Earth. The matter inside it is so densely packed that protons and electrons have been forced together into neutrons, giving the body its name. Such densities lie far beyond anything found in any laboratory on our small, calm world. To imagine a neutron star is to imagine the gentle, glowing soul of a once vast giant star, now compressed into a single, small, slowly cooling sphere drifting quietly through the long, dark cold of deep space across the patient ages of the wider galactic sky, glowing on softly in the calm distance of the stars. A single sugar cube of neutron star matter would weigh as much as a mountain. The matter inside a neutron star is so unimaginably dense that a single small piece the size of a sugar cube would weigh roughly as much as an entire mountain on Earth. To put it another way, a teaspoon of neutron star material would weigh somewhere around 1 billion tons, far more than every human being on the planet combined. This soft yet astonishing density is the result of the inward pull of gravity acting on a body that has lost the outward push of fusion energy. The neutron star is held together not by burning anything inside it, but by the strange quantum properties of neutrons themselves resisting further compression. To picture it is to picture a quiet city-sized sphere quietly carrying the weight of an entire star inside its small, calm, gently drifting cosmic body deep in space, slowly turning across the long, calm ages of the silent galactic dark. A pulsar is a spinning neutron star that softly sweeps a beam of radio light. Some neutron stars spin very rapidly and emit narrow beams of radio waves or other radiation from their magnetic poles, sweeping these beams across space the way a lighthouse sweeps light across a calm, dark sea. When such a beam happens to point briefly at the Earth during each spin, our radio telescopes detect a soft, regular pulse, and we call the star a pulsar. The first pulsar was discovered in 1967, and its very steady beat at first puzzled astronomers, who briefly considered whether it might be a signal from another civilization. It turned out to be the natural, slow ticking of a spinning neutron star left behind by a long-ago supernova. Each pulse we hear is the soft cosmic heartbeat of a giant star's quiet final remnant, gently calling out across deep space, a slow, quiet ticking from the long-ago end of one great star's bright life. Some pulsars spin hundreds of times every single second. The fastest known pulsars spin hundreds of times every single second, an almost impossibly rapid rotation for a body the size of a city carrying the mass of more than one Sunday. The fastest one yet discovered, called PSR J1748-2446 AD, completes a full rotation about 716 times per second. Yet despite this incredible speed, These stars are so smooth and so dense that their rotation remains remarkably stable across long stretches of time. To imagine such a body is to imagine a small, dense, almost perfectly round sphere quietly humming through space, spinning faster than any everyday object on Earth could possibly endure, while still drifting calmly through the long dark of the wider galaxy across many millions of slow, patient cosmic years of soft, ancient turning in the deep, silent body of the wider galactic sky. A magnetar is a rare neutron star with a magnetic field beyond imagining. Some neutron stars are wrapped in magnetic fields so powerful that astronomers have given them their own special name, magnetars. The magnetic field of a typical magnetar can be roughly 1,000 trillion times stronger than the Earth's own gentle magnetic field, far beyond anything we could ever build in a laboratory on our small, calm world. Such fields are so intense that they would severely disturb the structure of any matter brought even modestly close to the magnetar. Yet, from a great safe distance, magnetars are simply small, quiet, dense bodies drifting calmly through the long dark of space, occasionally sending out soft, brief flashes of high-energy radiation. They are among the most extraordinary remnants left behind by the slow, patient deaths of the most massive ancient giant stars in our wider neighborhood of the long galactic night. And from these strange spinning hearts, our path now turns to the deepest, quietest endings that the most massive stars can leave behind. The most massive giant stars collapse beyond neutrons into black holes. The very most massive giant stars do not end their lives as neutron stars at all, because their final iron cores are simply too heavy for even the strange resistance of neutrons to support against the inward pull of gravity. When such a star reaches the end of its life and undergoes core collapse, the center is squeezed past every known limit of matter, and the result is a stellar mass black hole. The black hole forms quietly inside the surrounding supernova explosion, a small region where gravity has become so strong that not even light itself can escape from inside its boundary. The death of a true giant star is, in this sense, the patient cosmic origin of one of the most extraordinary objects in the entire universe, hidden softly inside the soft glowing cloud of the dying star, slowly settling into the long, patient dark of the wider galactic sky. A stellar black hole is the silent grave of a once mighty star. A black hole left behind by the death of a giant star is in many ways the soft, silent grave of the original star. A quiet, small region of space where the entire compressed mass of the dying core has gathered into a single point of unimaginable density. Around this point lies a boundary called the event horizon, beyond which no signal of any kind, not even light, can ever return to the wider universe. From far away, the black hole reveals itself only by the gravitational pull it exerts on nearby gas and stars, gently bending their orbits or quietly drawing in any material that drifts too close. To imagine such an object is to imagine a calm, dark resting place at the very end of one giant star's long story, drifting silently through the patient body of the wider galaxy across long, dark, slow ages of cosmic time without ever again touching its old form, glowing only by the patient pull it still gently exerts on the dark. The event horizon is the soft edge from which not even light returns. The event horizon of a stellar mass black hole is a remarkably small body of space, often only a few tens of kilometers across, despite enclosing several solar masses of compressed matter. A black hole of perhaps 10 solar masses, for example, has an event horizon roughly 30 kilometers in diameter, similar in scale to a city or a small region of countryside. Inside that boundary, the inward pull of gravity becomes so steep that all paths through space and time bend inevitably toward the center, no matter which direction one might try to travel. Yet, from outside, the black hole itself is utterly invisible, a soft, silent absence in the wider sky. To picture an event horizon is to picture a calm, dark sphere quietly resting in the patient deep dark of space, a soft, small absence inside the wider body of the silent night sky, drifting on across the long, slow ages of cosmic time. Around many black holes, hot disks of gas glow softly in the dark. When a black hole has a nearby companion star, gas slowly drawn from that companion can spiral inward, gently forming a swirling glowing disk around the black hole called an accretion disk. As the gas in this disk falls inward, friction heats it to extreme temperatures, often glowing brightly in X-rays that astronomers can carefully detect from very far away. Many of the first black holes ever confirmed were discovered through their bright X-ray emission, including the famous source called Cygnus X1. From a great distance, the entire system looks softly luminous, even though the black hole itself remains utterly invisible. To imagine such a system is to imagine a slow, glowing whirlpool of light spinning gently around an unseen still center, quietly drifting through the patient deep dark of the wider galactic sky across long, slow ages of cosmic time. When two black holes meet, the universe rings with quiet gravitational waves. When two stellar mass black holes happen to orbit each other, they can slowly spiral inward over millions or billions of years, finally merging in a brief moment that sends powerful gravitational waves rippling outward through the very fabric of space and time. These waves were first directly detected in the year 2015 by the LIGO Observatory, almost 100 years after Albert Einstein first quietly predicted them in his theory of general relativity. Each detected merger is in some sense the long-delayed final act of two giant stars whose lives ended in the very deep cosmic past. Tonight, somewhere far beyond your eyes, gravitational waves from such mergers are quietly passing through the calm body of the Earth, very gently stretching and squeezing the soft space inside your patient's sleeping room, in long whispers of slow cosmic motion you cannot feel. And as you rest with these vast, patient ideas, let them settle gently like dust drifting through still moonlight. Take a soft breath, let your body grow heavier, and let these gentle science for sleep stories carry you a little closer to the slow, soft hours of true rest. Not every giant star ends in a violent supernova explosion. Not every giant star ends its long life in a fierce supernova explosion, because some of the lower mass giants follow a slower, gentler path toward their final state. Stars with masses roughly between 8/10 and 8 times the mass of our Sun grow into red giants as they age, but eventually they shed their outer layers in a much calmer way than a supernova, drifting them away as glowing, gentle shells called planetary nebulae. The hot, bare core left behind in the center slowly becomes a small, dense white dwarf rather than a neutron star or black hole. The whole quiet farewell can take 100,000 years or more, far slower than a supernova. To imagine it is to imagine a star softly breathing out its outer self into the wider galaxy across many quiet ages of slow, patient cosmic time, drifting gently into the long, deep dark across the soft, calm body of the wider sky. Some intermediate giants quietly puff off their outer layers as a planetary nebula. A planetary nebula is in many ways one of the most beautiful objects in the entire night sky, a soft glowing shell of gas slowly drifting outward from the dying core of an aging giant or middleweight star. The nebulae take many delicate shapes, from gentle rings to graceful butterflies to soft spheres, depending on the slow detail of how each star sheds its outer layers. The colors come from different elements glowing under the ultraviolet light of the small, hot remaining core, with oxygen often shining green and hydrogen often softly red. Astronomers can use the chemical mix of these slow nebulae to learn about the long inner life of the original star. To picture a planetary nebula is to picture a quiet final exhalation of a star, gently glowing in the deep, calm dark of space across many long, patient ages of slow drifting cosmic time. A planetary nebula has nothing to do with planets at all. Despite their soft, poetic name, Planetary nebulae have nothing at all to do with planets, and the term itself is in some ways a quiet historical accident. The early astronomers of the 1700s, especially William Herschel, used small telescopes to view these objects and noticed that their soft round shapes resembled the small disks of planets like Uranus, which Herschel had also discovered. So he simply called them planetary nebulae, and the name has gently remained ever since, even though we now understand them as the slow exhalations of dying stars. Today, the term is a soft reminder that science also carries with it the long history of how it was first quietly seen and named, even when the older meanings no longer perfectly describe the patient, drifting truth that lies behind them in the soft hush of the deep night sky above the calm, sleeping world below tonight. The Ring Nebula in Lyra is one of the most famous planetary nebulae in our sky. The Ring Nebula in the constellation Lyra is one of the most famous and easily observed planetary nebula in the entire northern sky, a soft glowing ring of gas roughly 2,500 light-years away from Earth. Through a small telescope, it appears as a softly luminous oval, faintly glowing against the dark background of space. The ring shape comes from looking through a slow, expanding shell of gas that surrounds the small, hot remaining core of the original star, with the outer parts brighter than the center because there is more gas to glow there. The Ring Nebula is the calm, slow farewell of a star a little less than twice the mass of our Sun, gently fading from the sky over many thousands of patient cosmic years as the star quietly completes its slow, soft, final farewell in the deep, calm dark of space far above us tonight in the long hush of the wider patient sky. The Helix Nebula looks softly like a great glowing eye watching the dark. The Helix Nebula in the constellation Aquarius is another famous planetary nebula, sometimes affectionately called the Eye of God or the Eye of Sauron because of its striking, soft, glowing eye-like shape. It lies roughly 700 light-years from Earth, making it one of the closest planetary nebulae to our small, calm world, and through a careful telescope it shows beautiful detail in slow, expanding rings of gas. At the very center sits a small, hot, white dwarf, the slow remains of the original star whose long life ended only a few thousand years ago in this gentle exhalation. To imagine the helix is to imagine a soft glowing eye open quietly across the long, deep dark of space, calmly watching the wider universe through the patient hush of cosmic time across many slow, drifting ages of soft and silent cosmic dark, glowing on patiently far above any sleeping eye. And from these soft glowing rings, our journey now turns to the quiet white dwarfs that lie at their hearts. At the center of every planetary nebula lies a small, hot white dwarf star. At the very heart of every planetary nebula sits a small, intensely hot, dense object called a white dwarf, the slow remains of the original star's compressed inner core. A white dwarf typically holds about half the mass of our Sun packed into a body roughly the size of the Earth, with surface temperatures that can reach 100,000 degrees in the early years after its formation. The white dwarf no longer fuses any new elements, but slowly cools by gently radiating its leftover heat into the surrounding cool dark of space. To imagine such an object is to imagine a soft, glowing leftover ember sitting calmly at the center of the slow drifting nebula it once belonged to, gently shining its quiet light into the long, dark, patient body of the wider galactic sky across the long biliations. Slow ages of cosmic time, glowing softly long after its first long bright life has ended. A white dwarf is the slowly cooling core of a once mighty giant star. A white dwarf is supported against gravity not by ongoing fusion, but by a strange quantum effect called electron degeneracy pressure, in which the electrons inside the body resist being squeezed into smaller and smaller volumes. This soft inner pressure can hold up bodies as massive as roughly 1 4/10 times the mass of our Sun, a careful threshold that astronomers call the Chandrasekhar limit. Beyond that threshold, even electron pressure cannot resist gravity anymore, and the white dwarf cannot remain stable. Within the limit, however, the body simply cools slowly across enormous spans of cosmic time. To picture a white dwarf is to picture a small, dense, glowing core resting peacefully in the long, deep dark, slowly losing its heat across many billions of patient ages of the long, calm cosmic dark above any small sleeping world, glowing on softly without ever fully fading from the wider sky. White dwarfs can keep softly glowing for billions of years. The cooling of a white dwarf is one of the slowest, calmest processes in the entire universe, taking many billions of years for even a noticeable change in its surface temperature. The smallest, oldest white dwarfs in our galaxy have been cooling for almost the entire age of the universe so far, and yet they still glow softly with the leftover warmth of their distant origin. The very oldest may eventually cool completely into dark, quiet objects called black dwarfs, although the time required for this is so long that no true black dwarf is yet thought to exist anywhere in the cosmos. To imagine the future of a white dwarf is to imagine a small ember resting peacefully in the long dark, slowly losing its heat across spans of time so vast that they dwarf even the present age of the universe, glowing on softly through ages much longer than any human story or memory can comfortably hold tonight. The very oldest white dwarfs eventually fade into cold, dark embers. Eventually, in a very distant cosmic future, every white dwarf is expected to slowly fade into a cold, dark cinder of carbon and oxygen, a small dents left over that no longer glows in any wavelength visible to human eyes. These hypothetical bodies are called black dwarfs, and they would represent the final calm state of most stars that ever lived in the universe, including our own Sunday. Yet, because the cooling time required to reach this state is far longer than the present age of the universe, no true black dwarf is thought to exist yet anywhere in the cosmos. The first ones may slowly form trillions of years from now, in a future so far away that no human language can fully hold it, drifting calmly through the long dark of the future cosmic night, gently waiting in the soft, patient hush of an age so far away that no human language can fully hold it. Some white dwarfs in close pairs can flare into a special kind of supernova. If a white dwarf in a binary system slowly draws gas from a nearby companion star, it can gradually grow heavier over time, eventually approaching that careful Chandrasekhar limit of about 1 4/10 solar masses. When it crosses this gentle threshold, the white dwarf undergoes a runaway thermonuclear explosion, briefly outshining its host galaxy in what astronomers call a Type 1a supernova. These supernovae are very useful to astronomy because they all reach roughly the same brightness, allowing them to act as careful cosmic mile markers across vast distances of space. Through them, the slow drifting end of one quiet white dwarf becomes a soft luminous tool for measuring the size and the slow expansion of the entire wider universe across the long, calm ages of cosmic time, gently turning the death of one small star into a soft cosmic ruler. And from these slow, soft endings, our path now turns to the deep gift that every giant star quietly leaves behind. Almost every element heavier than helium was forged inside a giant star. Almost every chemical element heavier than helium in the entire universe was forged inside a giant star, either during its long, calm fusion life or during the brief, intense moments of its final supernova explosion. The early universe contained almost only hydrogen and helium, with a tiny trace of lithium and nothing heavier than that. Carbon, nitrogen, oxygen, magnesium, silicon, iron, gold, and many others were all slowly built up inside generations of giant stars and gently scattered into space when those stars died. So the entire periodic table beyond the lightest few rows is, in a soft sense, the the long patient work of generations of giant stars across many billions of cosmic years, slowly enriching the wider galaxy with the slow, glowing material from which planets and oceans and breathing bodies will one day form across the long, patient ages of the wider, drifting cosmic body of the universe. The carbon in your body was once made in the heart of an ancient giant. The carbon in your body, the same element that forms the slow, patient backbone of every protein, sugar, and strand of DNA, was forged inside the cores of long-ago giant stars and gently scattered into the cool dark of space when those stars finally died. The carbon atoms in your bones, your skin, your soft beating heart, all once lived inside a giant star somewhere in the distant cosmic past. Each of them has drifted across long ages of cosmic time, gathered into a cool cloud of dust and gas, and slowly become part of a newborn planet, an ocean, a plant, an animal, and finally, part of the patient body that now rests softly beneath a warm blanket. You are, in this soft, true sense, a quiet living gathering of long-ago star carbon, slowly woven across many patient cosmic ages into the calm patient body, softly resting beneath your warm blanket tonight. The oxygen you breathe was forged long ago in the core of a dying star. The oxygen you quietly breathe in and out, with every soft, slow rise and fall of your chest tonight, was also forged inside the cores of giant stars long before the Earth was born. Oxygen is one of the elements made in the late fusion stages of a massive giant, deep inside its onion-like layers, and then gently scattered into the wider cosmos by its final supernova explosion. The oxygen atoms in the calm air around you tonight, in the slow, patient ocean, in every river and lake on the surface of our small, calm world, all began their long story inside the deep, glowing heart of an ancient star. Each gentle breath you take is, in this soft sense, a small, quiet thread connecting you to the long, patient work of giant stars far across the long, deep, ancient cosmic past, flowing softly in and out across the calm, slow hours of the night beneath your warm blanket. The iron in your blood was scattered into space by an ancient supernova. The iron quietly carried in the hemoglobin of your red blood cells, the same element that gives blood its soft, warm color and allows it to gather and carry oxygen through your body, was also forged inside the cores of giant stars long ago. Iron is the very last element built up by ordinary fusion in the heart of a dying massive giant, just before that giant ends its long life in a brilliant supernova. Each iron atom in your blood, in every slow, patient pulse of your wrist, every soft heartbeat through the long, calm hours of the night, was once part of the deep, glowing core of an ancient cosmic giant. Inside your own resting body tonight, the long, patient memory of vanished giant stars is gently flowing through every soft, calm vein, glowing on quietly in the small, slow rhythm of your sleeping heart across the calm, deep hush of the night above any patient sleeping world. The gold in a quiet ring may have been born in a neutron star collision. The very heaviest elements in the universe, including gold, platinum, and uranium, are not made inside ordinary stars at all, but in even more extreme cosmic events, such as the merger of two neutron stars left behind by long-ago giant supernovae. When two neutron stars finally spiral inward and collide after millions or billions of years, they release a brief, intense burst of high-energy radiation and gently scatter heavy element-rich material outward into space. Some of that material may eventually find its way into newly forming worlds. So even the soft glow of a small piece of gold jewelry on Earth carries with it the very long, very deep history of a pair of ancient giant stars whose patient deaths quietly forged the precious atoms inside it across vast spans of cosmic time and the long, slow turning of the deep, calm dark above any human shore. And from this soft, intimate gift of stardust, our journey now turns to the long companionship between giant stars and the worlds that orbit them. Many giant stars live with one or more close stellar companions. Most giant stars are not lonely lights drifting on their own through the dark, but instead live in close pairs or small groups of stars, all gravitationally tied together in long, calm orbits around a common center. These are called binary or multiple star systems, and they are very common in the upper mass range of the stellar family. Astronomers estimate that more than 70% of all massive stars in our galaxy belong to such systems, often spending their long lives quietly circling a sibling. The two giants in such a pair can have very different masses and very different fates, even though they were born from the same patient cosmic cloud at almost exactly the same moment. To imagine them is to imagine two slow glowing bodies softly dancing around each other across enormous spans of patient cosmic time, gently held together by the slow, patient pull of their own shared gravity in the deep dark. Mass can flow softly from one close giant star to its quieter partner. In a close binary system of giant stars, mass can slowly transfer from one star to the other across long stretches of cosmic time, gently reshaping both bodies as the gas drifts gradually from one to the other. When one star expands into a red giant, its outer layers can quietly spill across the boundary between the two stars and be drawn slowly inward by the gravity of the companion. The receiving star may grow larger and brighter, while the donating star may slowly shrink and reveal its hot inner core. Whole new families of stars, including blue stragglers and certain kinds of strange variable stars, are believed to form through this slow, patient mass transfer. To imagine it is to imagine a soft, glowing river of gas slowly drifting between two old companion stars across the patient ages of the wider cosmos, gently shaping each one into something new across the long, deep dark. Some massive binary stars are destined to one day spiral into one another. Sometimes two giant stars in a close binary system slowly spiral inward toward each other across millions of years, gradually losing energy through the soft gravitational waves they emit and through frictional drag if they share a common envelope of gas. In the very final stages, the two stars can merge into a single more massive body, releasing a brief burst of energy and reshuffling their inner layers in a sudden cosmic event. Such mergers are thought to produce certain unusual classes of stars, including some bright blue giants whose mass and brightness are otherwise difficult to explain. To imagine such a merger is to imagine two long companion stars finally drifting calmly into a single shared body, gently completing their long shared journey across the patient cosmic ages of the wider galaxy at last, drifting calmly into one shared body in the soft, deep dark. Hot blue giants sometimes carve glowing bubbles into the gas around them. The fierce ultraviolet light and powerful stellar winds of young blue giant stars do not just shine outward into the wider galaxy. They also slowly carve enormous bubbles of hot gas inside the cool clouds where the stars were born. Over a few million years, a cluster of young massive stars can clear out a region of cool molecular gas many tens of light years across, leaving behind a softly glowing cavity surrounded by the slowly compressed shells of the original cool nursery cloud. These soft bubbles, often visible in long, beautiful infrared images, are quietly reshaping the structure of entire star-forming regions across the long ages of cosmic time. To imagine them is to imagine huge, slow, soft pockets of warm space gently growing inside the cool, dark dust of the wider patient galactic body, slowly reshaping the long story of stars across the long ages of cosmic time. Giant stars rarely keep their planets calm as they age and swell. Giant stars rarely keep planets calm and stable for very long because their fierce light, strong winds, and short lifetimes all create challenging conditions for any planetary system that may try to form around them. Even when planets do gather in the cool outer disk of a giant star's birth, they often must endure intense radiation, gentle but constant orbital changes. and the eventual fierce final stages of the star's own old age. By the time a giant star ends its life as a supernova or a planetary nebula, any nearby planets are likely transformed beyond recognition. In this sleep documentary about giant stars, that quiet picture is a soft reminder that the long, calm conditions of our small home Earth around the calm, gentle yellow sun are themselves a soft cosmic gift not lightly given by any star, very patiently held inside the long, soft hush of the wider galactic dark. And from the slow drama of stars and their worlds, our journey now turns to the quiet ways humans have learned to read the lives of these distant fires. Astronomers learn the life story of a giant star by carefully studying its color. Astronomers learn an enormous amount about giant stars simply by studying their colors, because the color of starlight carries soft, careful information about temperature, chemical composition, and motion through space. By spreading the light of a star into a soft rainbow with a tool called a spectrograph, scientists can read its inner story almost like a quiet written page. Dark lines in the spectrum reveal the elements present in the star's atmosphere, while gentle shifts of those lines toward the red or blue tell of the star's motion toward or away from us. From a careful spectrum alone, an astronomer can often estimate a giant star's mass, age, surface temperature, and even its likely future, all from the soft, patient light it has sent quietly drifting across many calm light years of space. Finding our small, calm world long after that light first softly left the patient body of the star. The Hertzsprung-Russell diagram softly maps the lives of stars on a single chart. The Hertzsprung-Russell diagram, often called simply the HR diagram, is one of the most beloved tools in all of stellar astronomy. A soft, careful chart on which the brightness of stars is plotted against their surface temperature. Most stars fall along a long diagonal band called the main sequence, where they spend the calm middle of their lives quietly fusing hydrogen into helium. Giant stars, however, drift up and to the right of this main band, into the soft regions known as the giant branch and the supergiant branch. Each star slowly traces a careful path across the HR diagram during its long life, moving from one calm region to another as it ages, very gently writing its own quiet story in light across this soft inner map of the wider stellar family, slowly drifting from one calm region to another over the long, patient ages of cosmic time. Modern telescopes can quietly listen for tiny pulses inside a giant star. In recent decades, astronomers have developed a beautiful new way to study the deep inside of stars called asteroseismology, the careful measurement of the slow vibrations and pulsations that ripple gently through a giant star's body. Just as earthquakes carry soft information about the inner structure of our small, calm planet, the natural vibrations of a star carry careful information about its inner layers, its rotation, and even the structure of its hidden core. By watching the brightness of a giant star very carefully over long stretches of time, scientists can quietly read these gentle inner notes and softly map out the inside of a star that lies many light years away from any human eye, gently listening across the long, patient distance of cosmic space to the slow inner music of stars whose surfaces lie far beyond the reach of any direct human eye. Spectroscopy reads the soft fingerprint of every element inside a star. Spectroscopy, the patient study of the soft rainbow of light coming from a star, has been the gentle backbone of stellar astronomy for more than 100 years. With careful spectroscopy, scientists discovered that the same chemical elements found on Earth are also present in the atmospheres of giant stars far across our galaxy. The very element helium was actually first detected in the soft spectrum of our own Sun in 1868, before it was ever found in any laboratory on the surface of the Earth itself. The careful unfolding of starlight into its slow, patient colors has quietly shown us, again and again, that the universe shares one calm, soft language of physics, gently spoken in the same elements acro, The James Webb Space Telescope is helping us watch giant stars in distant galaxies. The James Webb Space Telescope, often simply called Webb, is a great modern observatory carefully positioned far beyond the orbit of the Moon, gently watching the universe in soft infrared light. Among many other discoveries, Webb has gently studied giant stars in distant galaxies, peering into nurseries of newborn massive stars and softly recording the dust-enriched atmospheres of old red supergiants. The infrared light Webb gathers slips quietly through clouds of cosmic dust that often hide visible light, allowing astronomers to softly see giant stars that would otherwise remain invisible to our small, calm world. Each careful image is a soft, patient new chapter in the long, slow human story of quietly understanding the lives of giant stars across the long, calm distance of cosmic space and the slow, deep ages of the patient cosmic dark. And as you rest with these soft, far-reaching wonders, there is no need to carry any of them with you tonight. Let them settle softly like quiet snowfall on a sleeping field. Take one slow breath in, let it gently out, and let these facts to fall asleep to ease you into deeper rest. The heaviest stars in the universe are also among the rarest. The very heaviest stars are the rarest of all, because the cool molecular clouds that give birth to them are uncommon, and because the most massive stars live such brief lives that few exist at any one time across the wider galaxy. For every very heavy giant in the Milky Way today, there may be hundreds of thousands of small, calm red dwarfs quietly drifting through the long galactic dark. The brightest stars in the sky are in this sense a soft, careful exception, not the rule, of stellar life. To imagine the wider galaxy is to imagine a quiet sea of small, dim, glowing bodies, with only a small, scattered few rare, bright giants gleaming softly above them in the long, deep, dark, like a calm ocean lit gently by a small handful of widely spaced, beautiful, soft cosmic lighthouses across the patient body of space, each one quietly glowing on through long ages of slow cosmic time. Most giant stars hide quietly within busy, crowded star clusters. Most giant stars are not scattered randomly across the galaxy on their own, but instead live tucked carefully inside groups called star clusters, where they were born together from the same patient cosmic cloud and have remained gently bound together ever since. Some of these clusters are loose and young, called open clusters, drifting through the disk of the Milky Way for only a few 100 million years before slowly dispersing. Others are tight and ancient, called globular clusters, holding tens or hundreds of thousands of older stars in beautiful round shapes around the outer regions of the galaxy. To picture a star cluster is to picture a quiet small family of stars softly traveling together through the long, slow ages of cosmic time, gently held by their shared gravity in the deep, patient dark of the wider drifting body of the calm galactic night. Open clusters often glow with the bright blue light of young giants. Open clusters in the disk of the Milky Way are often soft glowing nurseries of young blue giants, the bright, sharp white-blue stars that have only recently formed from a shared cool cloud of gas and dust. Famous examples include the Pleiades and the Hyades, both visible to the unaided eye on calm, dark nights, gently glowing as soft, small groupings of stars in the slow, patient body of the wider galactic sky. The blue giants in such clusters are short-lived by cosmic standards, often lasting only a few tens of millions of years before ending in supernovae or settling into giant phases. Yet for that brief moment of cosmic time, they shine softly as a quiet, beautiful family of bright young giants, glowing gently together in the long, deep dark of the wider galaxy above any sleeping world, slowly drifting through the calm, patient ages of cosmic time as a quiet, small family of bright young stars. Globular clusters hold many old red giants in their soft, ancient cores. Globular clusters, by contrast, are very ancient gatherings of stars that formed near the very beginning of our galaxy, and many of their original heavy giants have already long ago ended their bright lives. What remains today are mostly older, cooler red giants, slowly burning the late stages of their fusion in the calm orbits of these tightly packed cosmic groups. Some globular clusters, such as Omega Centauri or the Great Cluster in Hercules, hold roughly 1 million stars within a sphere only 100 or so light-years across, glowing softly as one of the most beautiful sights in the entire night sky. To imagine such a cluster is to imagine a small, dense, glowing globe of gentle old red and orange suns quietly drifting through the long ages of the wider galaxy across the deep, cosmic dark, slowly turning across many billions of years of patient cosmic time. The brightest single stars in nearby galaxies are nearly always giants. The brightest stars in nearby galaxies are nearly always giants of one kind or another, because only a giant can shine brightly enough to be seen from such enormous distances across the deep dark of intergalactic space. When you look up tonight at the soft glow of the Andromeda Galaxy, more than 2.5 million light-years away, the bright tiny points sparkling along its long arms are blue and red supergiants, each one perhaps thousands or millions of times brighter than our calm yellow Sunday. Even the small fuzzy patches of distant galaxies you may glimpse on a very dark night are quietly lit by their own great cosmic crowds of giant stars, glowing softly above your patient sleeping head across the long, deep bedtime, ancient dark of the wider universe, each one a quiet, far cosmic crowd of giant suns shining gently across the long, calm ages of the deep night sky. And from these crowded, glowing nurseries, our path now turns to the slow place giant stars hold within the wider story of the cosmos. Giant stars are the loud, brief poets of every galaxy in the universe. Giant stars play a strange, beautiful role in the long story of the universe because they are at once loud, brief, and creative. Glowing intensely for only a few million years, yet quietly forging the heavy elements, without which planets and life could never have come into being. They are the brief poetic verses written across the long, calm prose of cosmic time, the bright, small chapters whose patient consequences ripple onward through every generation of younger stars and worlds that follow them. Without giants, the universe would still be made almost entirely of hydrogen and helium, and there would be no carbon, no oxygen, no iron, no slow, patient world like our own. The brief, loud lives of giants softly carry the slow, patient creativity of the entire cosmos quietly forward into the long, calm future, gently writing the slow chemical story of the wider universe across many billions of years. Without giant stars, the universe would have no heavy elements at all. Without the slow, patient work of generations of dying giant stars, the universe today would still contain almost only hydrogen and helium, the two simplest elements, with the smallest trace of lithium, and almost nothing else heavier than that. There would be no carbon, no oxygen, no silicon, no iron, no gold, and no rocky planets like the small, calm Earth on which all of this is gently being said. There would be no oceans, no breath, no soft beating hearts. Every giant star that has ever quietly lived and died across the long ages of cosmic time has added another small, soft thread to the slow, patient chemistry of the wider universe, gently shaping it into a place where small, calm, patient sleeping bodies can softly exist and rest in the deep, dark, gentle hush of the night, very quietly carrying inside themselves the long, slow, patient memory of countless dying giant stars. The first stars in the universe were almost certainly massive giants. The very first stars ever to shine in the universe, often called population 3 stars, are widely thought to have been giants and supergiants made almost entirely of hydrogen and helium, since no heavier elements yet existed in the cosmos. These ancient giants were probably hundreds of times the mass of our Sun, glowing fiercely for only a few million years before ending in dramatic supernovae that scattered the very first heavier elements outward into the slow dark of the early universe. None of these original first stars are believed to still exist today, having all ended their lives in the deep cosmic past. Yet every star and every world that exists now, including the small, calm Earth, owes its very chemistry to the soft, patient first work of those very ancient lost giants of cosmic dawn, slowly handed forward across many billions of years into the small, calm body of every world we know today. Each new generation of giant stars enriches the gas of the next. Every new generation of giant stars slowly enriches the wider galaxy a little further, gently adding new, heavier elements forged inside its long fusion life and scattered outward by its eventual death. The first generation of giants made the lightest of the heavier elements. The second generation built upon their patient work, and each later generation has added a little more chemical complexity to the slow, patient body of the wider cosmic dust and gas. Our own Sun belongs to one of the later generations, born from a cool cloud already enriched by the long, quiet work of countless older dying giant stars. The slow, patient story of the cosmos, in this soft sense, is the story of giants slowly handing the heavier elements forward across the long, deep ages of the wider, calm, cosmic dark night, gently passing the slow chemical work of the cosmos from one generation of stars to the next, across many billions of years. To watch a giant star is to watch the slow heartbeat of the cosmos itself. In the soft hush of this sleep documentary about the lives of giant stars, the slow patient story we have followed tonight is in many ways the slow heartbeat of the wider cosmos itself, beating very gently across many billions of years. Giant stars are born, grow brighter, swell into red giants, end in beautiful supernovae or quiet planetary nebulae, scatter their elements into the cool, dark, and quietly seed the next slow patient generation of worlds and lives. The whole long, calm pattern unfolds again and again in different corners of the wider galaxy across the long, deep ages of cosmic time. To rest beneath such a sky tonight is to rest very gently inside the soft, slow rhythm of that great patient cosmic story, glowing softly far above your calm, sleeping body in the deep, gentle hush of the night, while you rest inside the long, soft, ancient story of giant stars in this sleep documentary. And so our quiet journey through the long life of a giant star begins to fade gently into the stillness of the night. From the cold, dark cloud where a star is first stirred into being through the bright blue middle years of fusion into the swollen red supergiant skies of old age and onward to the soft glow of planetary nebulae, the silent grave of a black hole, and the scattered stardust that becomes the next world, this sleep documentary has carried us softly through the entire long arc of a single mighty star. If these facts to fall asleep to have helped your night feel a little softer, you are warmly invited to come back to Drowsy Discovery whenever the world feels too bright or too loud. Subscribe quietly if you wish. Share these gentle bedtime stories with anyone in need of slower nights. And remember that there are always more wonders waiting for the next sleepy science journey. Right now, as you lie here in the dark, the carbon in your bones, the oxygen in your breath, and the iron quietly moving through your blood are all old gifts forged inside the heart of an ancient giant star and scattered softly across the universe long before this earth was ever made. Let your eyes grow heavy, and let them close if they wish. Let the rhythm of your breath become slow and steady, like the slow turning of a vast red giant in the deep, cold dark. Let your shoulders settle. Let your jaw soften. Let your hands fall open against the bed, and let the long weight of the day slip quietly away into the calm space all around you. Tonight, as you rest, the giant stars continue their slow, patient work. Out among the constellations, blue supergiants are burning quietly through their brief young years. Red supergiants are softly pulsing in the dark. Planetary nebulae are gently glowing around their tiny white dwarfs. And, somewhere in a distant galaxy, a single dying giant is scattering fresh stardust into the night. You are a small, warm presence within this vast, breathing universe of giant stars, peacefully resting among the wonders. Sleep well, sweet dreams. And may you carry with you the quiet knowledge that the very atoms of your body once shone for millions of years inside the burning heart of a great star, and that the universe has been gently growing softer ever since. This has been Drowsy Discovery. Good night.